Hello and welcome to this third in a set of videos on elementary hydraulic circuits. We'll pick up where we left off. What we want to look at here as a final topic in this area is where do we put a filter in a hydraulic circuit. And the filter symbol is this diamond-shaped symbol here with the screen shown, I guess you would say. So what we've shown here is we have the filter on the suction line of the pump. So what's the good and the bad of that? In this position, it's always good to put a filter upstream of a piece of equipment because then it protects that piece of equipment. So here we are actually protecting the pump. But that does not come without a price to pay. So we have a pressure drop across the filter. And this could actually, so what's going to happen, we're already going to have a lower pressure at the inlet of the pump than we'd have down in the tank because of the vertical distance between the fluid and the pump. So what you want to avoid is you want to avoid cavitation. And putting this filter here, usually the pressure drop across the filter is not great. But as the filter gets dirty, then the pressure drop becomes greater and greater and greater, and so you could actually have a case where you have a dirty filter and you have such a pressure drop that you actually cavitate your pump. Okay, so what happens is if you get too low of a pressure in the suction of the pump is the fluid can vaporize and make little bubbles, and then those bubbles can cavitate the pump. So this is a picture actually of a lobe pump that has had cavitation damage. So on the suction side of this pump, for one reason or another, the pressure was too low. The fluid vaporized, and then when you start compressing it in the pump, the bubbles collapse and they actually erode the pieces of the pipe. Okay, so you want to avoid that at all costs. So that's a disadvantage of putting the filter upstream of the pump. One good thing about putting the pressure or the filter upstream of the pump is that it's a low pressure line, and so you can use a low pressure filter, which often looks like a regular oil filter on a car. Those are not pressurized filters, so at a low pressure you can use a low pressure filter, which are much cheaper than a high pressure filter. Okay. Now you can put, if you want to avoid the cavitation, obviously, you can put the filter on the discharge side of the pump. Problem is, it doesn't protect the pump, okay, from any kind of trash or contamination in the fluid in the reservoir. So that's the danger. It does protect, though, the directional control valve and the pressure relief valve. Oh, that should be an R there, sorry. Which are expensive, delicate pieces of equipment, often with small passageways in them, so they're vulnerable to damage or clogging by contamination. Problem is you have to have a more expensive filter. So you need a high pressure filter, which is a more expensive proposition than a low pressure filter. It doesn't contribute to pump damage from cavitation, so you don't have any pressure drop across the filter and the suction line of the pump. We could also put the filter on the return line back to the reservoir. Now, the good part about that is in the low pressure part of the circuit, so you only need a low pressure filter again. Okay. It also does not contribute to pump damage from cavitation. You don't have a filter with a pressure drop on the suction line of the pump, but it doesn't protect your delicate pieces of equipment, either your valves. It's only filtering out the contaminants that you get as the fluid returns back to the reservoir. So that's the detraction or the disadvantage of this type of filter, or this placement of the filter in the line. Now let's look at another problem too. This is a standard scenario here. We have a not a single acting cylinder, but a double acting cylinder. And what I mean by that is from the pump you can actually feed the fluid into the cap end of the cylinder, or so that would be this envelope, and that would extend the cylinder. So this is the extension envelope. Or you can actually feed the fluid into the rod end of the cylinder to retract it. So we don't have that spring retract like we had before. This is a little bit more complicated because you got to provide a pressure connection to both ends of the cylinder. But what we'll need, we have a closed center here, and with a closed center, even in this position here, we'll have to provide a relief path for the fluid back to the tank. So if we extend the cylinder, when the piston gets to the end of its stroke, then you're going to have a closed volume again, and the fluid has to have some place to go, so you have your relief circuit there. And by the same token, if you retract the cylinder, when the piston gets over on the left-hand end of the, bottoms out on the left-hand end of the cylinder, you're going to have a closed volume there, and so you have to have a relief path. So in any one of these three envelopes, you'll need a relief path when you're at the end of the strokes on the outside envelopes, and just it's blocked here. The problem with this is the following. You're actually pressurizing this fluid, so the pump is doing the work to pressurize the fluid, and then you're just relieving it. Now when you generate pressure in a fluid, of course it takes energy to do that, so you're burning up energy just to produce pressure that you then just dump through a relief valve. So it's a waste of energy. It's not an economical way to operate. It's good that it protects the system, but it's bad in that you're burning up energy even when you're sitting still not doing any work. So there's ways to deal with that. This is our full pressure here. This pilot line pushes the envelope down so that we have a flow through the pressure relief valve into the tank. What we can do is we can add a check valve on the discharge line of the pump. So we're just flowing through there into our, well, when we're actuating or retracting, then the fluid would go on. So we have this is all pressurized here, but even, so let's say in this case where we're just sitting still, we're blocked, the center envelope is active, we're not actuating this valve at all. We wind up with a high pressure here. We have a check valve, so the fluid can go upward, but it can't go back. If we put a pilot line off of our pressure relief valve, and instead of just hooking it upstream of the pressure relief valve, we hook it to this pressurized part of the system, then the pressure here excuse me, will be held, and that will push this down, and then we have an open path between the pump to the tank. So if we're sitting in this position, we have pressurized, or in any one of the positions, it doesn't matter. As long as we pressurize the part of the system downstream of the check valve, that is what's going to open the relief valve, and then the pump is not pumping against any pressure, or very little pressure. It's not pumping against system pressure is what's happening. Okay, so this is a nice way. It's called an unloading circuit. The pump discharge is ported directly to the tank, so we don't have a big buildup of pressure here. We don't need it, and we can still have the system pressurized. And then we save the oil also from being heated up, and actually that's one of the primary ways to damage oil is to heat it up, to overheat it. All right, so there's other things that you can look at, other videos that you can watch on what's called the Big Bad Tech Channel by Jim Pytel from Columbia Gorge Community College. And then anyway, I've got some links here that you can watch, where you can watch these videos. Let's see. So I guess you can click on those. Even, well, if in the film you won't be able to click on them. And that's the end of this presentation. À la prochaine, which means until the next time.